Thank you very much for being here. My name is Vladimir Vishnevskii. I would like to offer the talk that is called Efficient and Reliable Wrapping of C APIs using modern C++. This would be a generic C++ talk where I would like to cover the architectural patterns and language features and standard facilities that can be used to adapt C APIs for reliable and convenient usage from C++ programs. And why this topic can be helpful, because it's one of the often use cases, yes, so that we are using C APIs from C++ programs. And in many cases, the introduction of some intermediate layer, some layer on top of C API can be necessary and beneficial. To elaborate on this, I would like to use an example, like a case. In this talk, it's LMDB. So this is a Lightning Memory Map Database Manager. This is an efficient key value store that is written in C and has the primary API in C. It's open source, and bindings are available in many different languages. We will look at some subset of this functionality just to see the typical features of C API. We will not be really focusing on this particular framework, but it will be very helpful. So for the examples of the C++ code that is used in this talk, some experimental framework that is available on GitHub was used. It was specifically developed for demonstration purposes, not the production-ready software. If someone is interested in contributing, their contributions are definitely welcomed. So now let's formalize a bit with our case, with the C API that we will be working on today. So instead of course, going through reference, let's just review some usage example to see what the C API of LMDB looks like. So as I mentioned, LMDB is a key value store. So multiple so-called LMDB databases, those are the key value tables, in fact. They can belong to environments. So there is some logical hierarchy where there's environment and multiple tables belong to this. So to start working with this storage, we first of all need to create an instance of environment. This is the C API that I'm used from C++. So there are there's a C++ syntax here. But first of all, we allocate the environment object. Then we can open the environment, because environment corresponds to some file system location where data and metadata is stored. So the allocated resource that we first retrieved, passing the pointer to pointer in the environment create function, we can now use to open it. And here we can pass some flags to open the environment. And some of them are interesting because we can specify that the environment can be opened in read-only mode, constraining it the way that only non-mutating operations will be available on the databases within this environment in our program. So so here I'm passing the flag that is absolutely irrelevant to this specific API. It's actually error code. Why? Because it's just a macro constant and the flags are represented as integers. So it's just passing here. So I'm making this mistake and I don't see that. Also, there is a fourth parameter that are the default file system permissions that will be assigned to the files created within the environment. I can also just misplace them. I just want to make a remark. So we are seeing here quite a typical features of C interface, but it's not anyhow a criticism of actually LMDB design and not a criticism of C language, because so we are using those cases and we see just the typical problems that we can see there. We know all the limitations that C language has. So if something is not working, already acquired resources are supposed to be disposed manually here. On every exit branch, we need to do that. So all the operations with the databases, they are happening under the transaction. Transaction should be created. Again, we are passing pointer to pointer. And this is how it is done. There are some irrelevant for our presentation parameters as well. And then the database can be opened. So we need to provide its name. Again, now we have already two resources to dispose if something is not working. And then we can put the values in our database using the function mdbput. By this moment, we need to have initialized environment transaction. We also need to open the database. This all, of course, is a client code responsibility here. And also this should be considered. The key and value, they are represented in C API in form of the void pointer and mv size that are fields in the structure called mdbval. So this is how these arbitrary data is abstracted in the C API. And this is a typical representation in C APIs. We use some helpers to convert from and to this mdbvals that, and the implementation of them is not that much important for us, but this is important how this is represented, how the data is represented. We can also get the data, so we can provide the key that is also in the form of mdbval, and it will be retrieved then. So we can also have continuous access to the database using the cursor mechanism. We need, again, to create the cursor, and then we can continuously access the items. So it can fit into the for loop. Again, this serialization, deserialization of the items, it's always performed in the client code. So what can we improve using some layer on top of what we just saw? Yes, so definitely would be good if we can improve code safety. Yes, so first of all, we cannot employ the type safety mechanism there. We also could use more, we could use safer resource management. This would give value to the implementation. Also, we see that some parameters, they are known at compile time, but they can be configured on compile time, and they can constrain our implementation in a way that we do not take the problems into runtime, like errors, for example, but actually resolve them in the compile time. Like, for example, read-only environment can, so if we open the environment in read-only mode, it can be configured actually not to have the methods that are providing the mutating access. We also, I'm sorry. It also would be good if we can provide compatibility with some C++ language constructs and standard facilities. This would significantly improve usability and reusability of our programs. And in general, improved readability, better structure would significantly would be beneficial. Plus, but if we would like to introduce some layer, yes, then we also need to understand, of course, what would be the final goal. Yes, so if we really want to develop the full language binding, or we just want to use some subset of the functionality that we'll be using, that we will wrap and to achieve some safety, for example, but there will be no reuse planned. Why? Because, of course, this full C++ binding and full language binding in general is a lot of engineering and a lot of effort. And most of the things that will be, so most of the examples, they will be going in the direction of full binding because it's more to demonstrate. But of course, in many cases, not environment, it's not required. And I will be showing also the examples and also highlighting on the techniques that can be used just not only just for making the bindings, but also for usage of the C code within the C++ programs. And also another question that is also important is that is dependency isolation, is the dependency to the C API isolation is required? Because this also to a very large extent affects how we will need to write the code. Because if we want to hide those dependencies in C++, in the source header and make it invisible completely, then we will be limited because a lot of meta-programming techniques will not be available for us then. But we will be, as I said, we will be going in the direction of binding, and let's review some usage example of some hypothetical design of the binding that we could elaborate. So here is some usage. First of all, of course, creation of the objects within the hierarchy. So we of course, fully hide all this multi-step initialization creation of the objects. They are just simply created by single methods. And they return, of course, we do not use any output parameters. We somehow return either objects or errors in this design. And what is also important is that the dependencies, they somehow are required to produce the dependent objects. So we structure the program that way that the internals are encapsulated and are sufficient to produce the dependent objects. For example, we have environment that here explicitly produces database. This can be designed another way, but in this way, it's just explicitly done explicitly done using the factory function. Also, operations that are required to be done in the presence of transaction are then becoming methods of the transaction object itself. So this means that we need transaction to really perform them. And of course, transaction encapsulates everything that is needed. So we structure the program in a way that the creation of the object becomes more described by our object model that we use. So we also operating with, not with the MDB vals or any abstractions that require serialization on the client side, but we actually operate with the types, and we can use, again, compile time mechanisms to specify the rules how we want those types to be translated into the C abstraction. So here we're providing some form of the trait. And also still, despite the fact that we can, sorry, one more thing. Yeah, so we also can specify here that the environment is supposed to be opened and read-only. That means that the environment will not contain any methods that would be leading to creation of read-write databases or allow any mutating operations on the environment objects and the objects that belong to the environment that it will produce. So, and despite of this configurability, we still, and compile time, we still can provide the types that will be used in our program. So for example, here we still have access to our transaction types, so the client code is not necessary, does not need to use the template metaprogramming and just can use the concrete type that can be resolved like this. Yeah, so the concrete types are available as netted aliases. Let's now go through this design and see what techniques were used and just look at them with more details. So first of all, we see that in this design that I proposed here, we have the functions, they return either errors or error codes. And the error codes, they can be identified using comparison with some error code enumerations that are available in our names in the namespace of our REPA. We can compare only error codes with those enumerations, so we use strong types here. And the simplest way to actually translate those error codes from C API to C++ API would be just to really use scoped enumeration with the underlying type that corresponds to the type that is used to report errors in our C API. We can then assign the values correspondingly, so from C API to the C++ scoped enumeration. And then what is convenient is that starting from C++ 17, we can then just explicitly create the enumeration from the underlying type. This has limitation that for this to be possible, we need to include the header of our C API into the header of our C++ API. So this can be, might be not acceptable if we need to isolate those dependencies for some reason. And then we need to translate those values. Unfortunately, here, there will be not that efficient, but there will be no other choice to do. Another thing that we should consider is that what is the way how we are passing those actually errors and propagating them from C API already to the client code. And we have many different ways, so not many, but several ways of in C++. Compared to C, because in C we typically use return code output parameters. In C++ we also can throw exceptions, and we also have now available also wrappers for return types or error types. And in my example, I was using std expected. So that is a convenient way of doing this. This is the facility that's available since C++ 23 that can either store a value of expected type or a value of an error type. Yeah, so this is some form of the facility that is a hybrid between optional and variant, and it has interface similar to optional, except that instead of being empty, it stores the value of an error type. It is, there are several backports available and alternatives for that. We can also use exceptions, yes. So, but in exception, we can implement our own that belongs to our repo, and anyway, we will probably need to steal the to store the error code, because this is the way how we can identify the error when it is propagated. If we use any exceptions, then we can code for positive case. So that means that it will make our implementation simpler. But in this simple example, this is really easy to write the exception safe code, but writing exception safe code is, in most of the case, requires some skills. So it would be fair to mention this. Advantage of exceptions is that they can be report errors in the functions that either do not have return type or they have predefined return type, and this is quite important. So we can throw it from constructors. We can also throw them from operators. We can, or from any arbitrary function. Yes, so some projects do not use exceptions or cannot use exceptions. There are industrial standards limitation regarding exceptions. There is still an argument about exceptions. And so important thing to consider that if exceptions are used as a standard mechanism to report and propagate the errors, there is a possibility that this binding will not be reusable then, because it cannot be used by the projects that do not allow exceptions for some reasons. Yes, so in general, this is important consideration for library developers. Using preprocessor facilities, it is possible to have some form of the configurable error reporting, or for, yeah, it solves some of the issues of compatibility with various standards, but it becomes a bit tricky, honestly speaking. Okay, so continuation of our topic with the error codes and strong types that we use. We also have in many C APIs, we have something like flags. Yeah? So the flags that are where we configure some properties, and they are typically encoded as integers. So there are a lot of APIs where there are multiple parameters that are encoded as integers, because we have booleans that are encoded as integers, flags as integers, yes. So there are, and also some integer values that are supposed to be integers. So again, to protect for some erroneous usage when we are specifying the properties, it would be good if we are using strong types here. Yes. So for example, here we again using the scoped enumeration, and it's not compatible with another template parameter that is number of databases would be available. So we cannot just accidentally misplace them. So to do this, we following the same pattern as with error codes. We specify the underlying type that is used for this flags in our C API, again assigning the values. And again, now it's finally in the standard. Since cplusplus 23, we have this to underline. This is a trivial utility that gets the that casts the scoped enumeration to the underlying type. We have this now available, but I'm sure that everyone had already this in their own utility libraries. But yeah, so good to know that it's there. So this is how we can then propagate the value that is strong and is safe for our client then to the C API itself. To have support for this bitwise operations that are typically used to combine several flags together, we need to provide the operators, the corresponding operators. So that means that there are no operators by default, and of course our scoped enumerations, they cannot be implicitly converted to integer, to the underlying type. So that means that we constrain what can be done with them, so in a way that only those operations that we would like to have are available. So there is this would be then this would add extra safety mechanism to the API. Now about overall object creation. Yes, so in our usage example, we saw that we use here the factories, or I used here the factories, and that produce the children now in the LMDB logical structure. Yes, so that this is the factory methods. This is not object-oriented design factory factory pattern. No polymorphism involved. It's just a function that produces another object. Yes, so it's a good way of creation of the object, because in the logical structure, when the parent has everything to produce the child, it preserves encapsulation very well. For example, here, environment to open the database, so it stores the property environment, it then can open the database, and everything that is needed for this operation, it already contains or can then create. So that means that we do not need to expose any internals. Then the object can be just simply created and returned and used. Plus, the factory functions, they are also they allow different error reporting mechanisms. So if we can return our std unexpected that we used before, or we can throw, we also can propagate compile time properties, because the return type can then be resolved based on the compile time parameters of the parent object. Alternative would be to use the explicit dependency in the constructor. Here, for example, we pass the environment object to database object. This also somehow describes the dependency, so we structure the program that way that it is clear that environment is required to create the database, but in this way, we need to expose some internals. For example, we need to have these low-level object from C API to use it for creation of our database. Alternative would be to set up these friends and to declare friendship. They are still, so the friendship's probably better because it still limits the exposure. In some cases, it is necessary. Okay. Another thing that I also wanted to also cover is a safe resource management. Yes, so we see that in our usage, we also do not do any manual resource disclosure. So because everything is handled by RAII pattern. So this is resource acquisition is an initialization pattern. That means that when we allocate some resource, we also create an object, a handler, and bind the lifetime of the resource with the lifetime of this object. So as soon as the object's lifetime ends, then the resource will be disposed. The minimalist implementation for pointer-like resources that we have in our example is to use a unique pointer with custom deleter. So here I specify deleter in the form of the functor, so the resource will be then disposed using corresponding API call. We can use the alias then and use this alias for handling those types of resources. So this is how we can do, and this is to implement this pattern, we have everything in standard library. Since C++20, we can just specify the type of the non-capturing lambda because the non-capturing lambda now got the since C++20 default constructible. So this is can be done even shorter. And the pattern to use this, it is typically like that. So we are just create the raw pointer, we pass the pointer to the C API that is supposed to allocate this resource. And then we pass it into the control of the handler that we specified. So since C++23, we have now helpers that simplify this a bit. So we have out pointer and in-out pointer adapters that produce the object of the type that is compatible with the pointer to pointer. And then that means that we can pass it directly to the function. And this makes this code shorter. And we also do not have a gap while we still have the pointer that is not under control of our handler. So in some APIs, and in our example as well, we have some objects and some resources that have different mutually exclusive termination states. For example, here we have transaction. There can be also some form of the allocated buffers that can be either sent or they can be discarded. This pattern works quite well with those type of resources, but we need to design our API in a way that after we receive the resources, those functions that perform, that actually represent those terminal states and do this processing, they consume this resource. Yes, so here we have commit of the transaction or the cancellation of the transaction requires that we pass this handler there as a right value reference. So that means that we need to explicitly move into this function, our handler. This makes the things clearer for reader because it shows that the resource is supposed to be consumed, and also makes it clearer for static analysis tooling as well. So, those things, they are very useful not only for the full bindings, but anywhere when we just use some C APIs where we have some resource when we need to handle. Those are, I think, quite an essential pattern generally to approach those problems. Also, one remark from my side regarding those lifetimes and objects. So we see that in our example, we have like environment, we have databases, and environment is supposed to be opened while we still have databases. So it looks like we can benefit from some shared ownership. So it might be, and definitely in some cases, if used properly, it can increase safety as well. But this also has runtime costs, and it's not necessarily will be used by the client. So I would really propose to start from the simple implementation that is essential and with minimized runtime overhead, and then either leave it to client or add some extras, extra functionality to have something that involves some runtime costs. So this is, I think, would be the proper approach for extending the library further if we are developing a library. Okay, now a couple of words about compile time configuration. So I mentioned this before, but we can take some parameters of our C API that are not supposed to be changed during the execution of the program to compile time. Specifically, I was mentioning this read-only property. Why it is beneficial? First of all, the compile time properties can be checked on compile time. For example, here we specify that our environment should be read-only and write-only, and this is wrong. It cannot be. So this will be a compile time problem. If this would be, and quite often we see in the documentation of C API that some flags are not supposed to be used together. So this can be then taken into compile time. We can check this and then provide the proper error, proper assertion here, or static assertion that this should not be done like this. So this will not cause then the runtime problem or some strange behavior, because this would be already identified during compile time. Another thing is that we can remove the whole class of programs when we try to mutate the objects in the environment here that are not supposed to be in the read-only environment. That is not supposed to be objects in which are not supposed to be modified. So again, in C APIs, because there are no other option, all those things are resolved in runtime. We could help ourselves here because the problem is that if we just disable the read-write functionality in the created environment, then we will be unable to do those kind of mistakes. Yeah, so this is a simple example where we just be disabling some part of the functionality. We can have some combination of the flags that can be used to adjust the interface. But for read-only thing, this is more or less straightforward. Let's go through that. But one important thing is that it still will be nice that despite of the, so that we still, depending on the compile time configuration, still provide those types. Because as I mentioned in the beginning, so the issue is that it's good when we can resolve them and still can write the programs that are dependent on those types without necessity to make those functions templates. So in our case, when we have some parts of the C API that can be so if we have some functionality that can be splitted and configured in the compile time, so we can just extract some common functionality. We can take the functionality that is then controlled by the flags into some splitted classes. In our case, we can have the read-only environment that has only type declarations and methods that correspond to read-only options here. So to read-only access. And we can then extend the read-only environment by read-write environment. This would make it possible that this would, so first of all, we will have only the proper methods in those classes, plus we will also have these nested declarations that are split depending on what type of environment do we have. This is an example. We can then resolve this in compile time, the type of the environment that should be returned using some compile time condition based on read-only property. Yeah? So here we check if the flags has the read-only flag set. So alternatively, if we do not need to have those different nested type declarations, we can just simply actually constrain our methods using requires keyword. We can say that our method is constrained to be available only if read-only property is not set. So this is available since C++20. Enable if were used before. So, and this is a good substitution for those patterns. So, one more thing to mention here is const-correctness of our wrapper code. So in interesting detail, the C functions, the standalone functions, they are standalone functions, and in many cases, they can actually be called from constant qualified methods of some class. Because quite often we just pass the parameters by value, so they are copied. That means that the constant qualification of the members of the class, the properties of the class, plays here no role. That means that this is important that the library developers, those who are developing the wrapper, taking care of this, and they're carefully assigning this constant property. Because here in this example, we have the drop method that can just remove the database, that is const qualified, and it will actually remove the database, so mutate the object that it models. If we're following the strategy, the recommended strategy that the objects, they model, that the constant correctness corresponds to the immutability of the object that the class models, then we should take care of, and of course drop cannot be constant. So this is what we want to enforce, is that constant qualified objects, like for example here, read-write environment but constant qualified, still does not allow any mutating operation. So that means that we cannot open the read-write database, so database in read-write mode in this environment. So if we correctly assign the constant qualification, this will be prevented. The next thing that I also wanted to mention is the C++ types adaptation. Yeah, so in our code, we are using just the normal types. We are not operating with abstractions. We are using integers. We are using strings, and the client should be protected from the C representation of this data. So in our example, the LMDB API, it works with some untyped abstractions. Yes, so we saw that there's void pointer and the size that used to propagate to specify the arbitrary data, and we need to provide the client API that is based on some concrete types. And this is quite a typical problem, because the client code would benefit if these translation and representation for the C API will be done by the wrapper code itself. Yes, and there will be no need to take care of this all the time in the client code. So in our case, if we use the compile time approach, yes, so we can specify a trait that will be taking care of this transformation or representation of the data from the C++ types that are used by the client code, or the custom types that client uses, to the representation that is accepted by the C API. The client, when specifying those rules, those are client-specific rules, should also be protected from usage of the C abstractions. In our case, for the client, the way how we can represent some byte representation of some data can be done using std span. Yeah, so the span of bytes is a low-level representation of the data that can be then forwarded to the wrapper that then will translate it into the MDB val. So those are and in our case, we can make an alias of byte span, that span of byte, that is also stores that is a constant view, so it's a mutable view into the bytes, because we are not modifying the data that we are pointing at. And because MDB val actually has non-constant pointer there internally in our implementation of the wrapper, we handle that. This is also a typical issue that the constant qualification can be a bit inconsistent. That means that for client code, the constant correctness should be enforced, but within the wrapping code, we can take care of the various inconsistencies. Here so the client code, when providing the representation in form of the byte span, provides the constant bytes, but we constant cast it here. The data will not be modified, so we will not. So it's not supposed to be modified. We will not go into undefined behavior, but we need to take. This is inconsistent, so that needs to be fixed in our implementation. This is a place where it can be done. And so generally, the client code can specify how to transfer from C++ types into the C representation using the trait, and there should be a separate trait for key and for value. So those are the rules, how to get the byte representation of the object and how from byte representation to get the object back. This is can be then defined. And one single trait, here uint32 trait, this is the one that used for key, has the methods to bytes and from bytes. And this byte span is used as a return value. So that means that the client code who specifies in which those rules are specified, it is not aware of the C abstraction here. So to have the bytes representation, this is also a nice facility that is available in C++20. As bytes, it converts the span to the byte span. This is convenient to use to get the byte representation of some object. And here, this function 2bytes, it returns the byte span. And as we write in the generic code, we can benefit from the feature that sometimes actually 2 bytes and this byte representation can involve more complex operations than just getting the byte view, because we can compress data, we can encode it somehow, and in some cases 2 bytes should return actually the storage, the allocated storage for this data. In this case, vector. Because we are writing generic code, we actually can treat those return types just as spans, take care of their lifetime, and then just propagate to the function. So here we call the trait 2 bytes functions for the key and for value. Then we use our helper that we saw before to convert it into C representation, MDBK and MDBval, that are not constant because they are not constant in C API. And then we just pass them here. Regardless of what was returned, span or vector, we take care of this. And after we call the put, the data was written there, and we have our data stored. To be more specific about those various traits, we can specify concepts that would provide a better description of the requirements to those traits, and also provide a better diagnostics if we do not fulfill some of those requirements. Yes, so for our deserialization traits, it should have a nested declaration of a value type, and also have the from bytes method that we saw before. For serialization trait, we need to have 2 bytes method that returns something that is convertible to byte span. This allows us to benefit from our generic code of our generic approach, because for the trivial copyable data, we can just use the byte view of this object. But for the more complex types that require some memory allocation, we then can still use the same code. Yeah. So what alternatives to this generic approach would be some solutions based on type erasure, where we provide some maybe STD functions that would be the conversions for us from some types to another types, to byte representations. But then we will need to use some common way of propagating those bytes. In most cases, so it probably that we will require to provide the serialization in form of something like vector that will own the memory in which the bytes will be allocated, and that would require, we will pay penalty for the type erasure. We'll also pay penalty for using for memory allocation. So that means that the generic approach in which we can actually still have the various handling for different types of objects is more beneficial, but it's not always possible. So the key trait, value trait, it's actually a combination of serialization trait, deserialization traits. This is how our concepts for key trait and value trait looks like. Some extras are possible that might be we need some extra constraints, but the key value trait is then contains the key and value trait. Yeah, so just a simple combination. There is one interesting feature that I also wanted to highlight. Quite often, we need to also deal with callbacks in C APIs. Yes, so the C APIs those callbacks, they also provide the data. They propagate the data to the client code, of course, using the C API abstractions. In our case, we can provide the callback to compare the keys. So some form of the custom comparison function. And in our implementation, this also can be done in a way, if we use a generic approach, we can also allow the client code to specify comparison function as a part of the trait. But this function from the trait, the presence of this function can then be detected again using this requires expression that is also can be used as a substitution for various detection idiom implementations. And if we have this comparison function so that we need to set up the callback, we can identify this in compile time and then actually set up the callback. If it was detected, we can use the setCompare function in our example. But we need to adapt our C++ callback to be compatible with C API. And for this, we can use the function template CMP that we instantiate with our trait, and it actually just propagates the call, so delegates the call to our trait CMP function, adapting the parameters. So that means that even if the callback is provided, the callback still operates with the C++ abstractions, but not with the C abstractions. So that's the way how this can be done. So we discussed the details of, so we discussed some of the techniques that are, they were actually increasing in complexity till now, and they will continue to increase in complexity. Some of them were essential, like, for example, type safety mechanisms that we could employ. Some were some topics like safe resource management. They are also helpful and even essential. We also saw how we can then protect the client code from operating with the C API abstractions. Now I would like to offer some of the ideas also that are a bit, that I would characterize as nice to have, but not essential. Yes, so let's see it like this. One of them is actually some form of the iteration support. Yes, so we saw that in our C API, we have continuous access to the data in the database. This is also can be continuous input operation. Yes, so something that we can do, for example, we can read data from some storage. We can actually work with some file system. We can also work with some not standard. We can also receive some data. In many ways, this can be seen as some form of the iteration, like input, and the abstraction for that is an input iteration. In our thing that in application for our LMDB facilities, we have this input operation that is implemented via cursor, where we can just continuously read the data. So here is the example, what we could achieve if we implement some form of the custom iterators and views. This would allow us to actually use the facilities to simply to the standard facilities with the data that we can retrieve from our API, C API. So we build a bridge between the standard library facilities and some language features, like, for example, range-based loop, implementing actually iterators and views. And in many cases, retrieving data from C API, this can be abstracted as the input iterator. The input iterator is a iterator category that's actually one of, so it's, I would say, so input and output iterators are the most basic ones. And to implement them, but to implement the iterators, we need to consider that the input operations of the API that we wrap, they can fail. That means that we need to have a mechanism to actually propagation the error reporting from the API. And there is, because we are using, because the C API is wrapped and the standard iterators, they are dependent on the operators overloading. Yes, so we then do not have this mechanism. That means that they're actually quite reliant on exceptions. And if we are not using exceptions, then we do not have a reliable, so we do not have a portable way, and actually we do not have a proper way of propagating the error to the client code from this low-level API that we try to wrap. And this is a limitation for those things. So, but if we are using exceptions and if we decide to use them in our API design in general, yes, so then we can implement the input iterator that supports the operations that we want to actually make available to the client code. Starting from C++20, we now have some requirements to the iterators described in the form of concepts. This is quite convenient because it is now in the code, we can see what iterators are supposed to support. Unfortunately, it's not all the requirements can be specified in form of the concepts, but in case of iterators, that's quite helpful. Some requirements are redundant, but generally we can see that it is supposed to be movable, it's supposed to be incrementable, we should have dereference operator supported. We can also use also static assert to actually verify that the class that we develop and want to make it iterator compatible to actually be conformant with the concept. Yeah, so when we're developing those. And this is helpful. And in our case, so to really have the implementation of the iterator, we need to, first of all, support some nested declaration, specify iterator category here, like it will be input iterator, then we need to provide the value type, difference type, and then we implement our functions, so the methods of the iterator, using, of course, this low-level API. In my case, there will be a function that will be calling the C API that's called navigate cursor. This can be also some read function or something like this. The iterator contains everything to perform this read operation. So in case of LMDB, navigate cursor operation is just MDB cursor get. When we initialize, we set up the cursor to point at the first record, and then we just move to the next one. And that's why we need operation parameter here. And then depending on what MDB cursor get returns, we either assign some item that we store in the iterator. We can reset this item if we reach the end, and we can throw exception if something is wrong. Then, of course, increment is implemented again using this function. With the MDB next parameter. And what is important, since C++20, the requirements to the input iterator, they were relaxed. Now there is no need to support the comparison between with another operator type. It's enough if there is an operator, a comparison operator with default sanctional type. So that means that so the input iterators will be compared with these sanctional type object, and the purpose of this function will be just return true when there is no possibility to read data anymore. So that means that input iterator implementation looks not that complex, but at the same time it enables the interoperability between then some low-level C API and standard facilities. If we have an iterator, we can also move forward towards range. So generally, ranges, the concept of the range is displayed here. So we need to be able to call begin and end with some type. And the ranges, they can be helpful because, again, we can then use our code with the range-based algorithms and range-based loops, for example. And again, we also have the concepts to describe what range should look like. It's also helpful because it also serves as documentation to some extent. And we also can verify that the types that the type we are developing corresponds to this concept and get better diagnostic if it's not. So the implementation would require that, in fact, we have only begin and end functions where we can return an iterator. And for the end, we are returning this default sentinel object type, so object. So this implementation also, there are some things, so there are some nuances to consider here, but generally the possibility to do that exists, and this is then quite beneficial because it improves usability and readability of the code. Yeah, so if range, in fact, is not supposed to have any state or own some low-level resources that we represent, so we can also use subrange because this is the facility that just stores the iterator and some form of the end sentinel object. In our case, this would be default sentinel here. So this can be done in a simple way if iterator contains everything that is needed here. So if the function returns already functional iterate. So if exceptions are not used, we can implement some methods that would be receiving the functors to process the data that we iterate over. In our case, we can have the API that would have iterator and iterate by key and other different iterator options where we pass some generic functor. We can also constrain those fun using concepts, but generally the idea is that we hide the implementation details of this iteration within our repo, but provide to the client possibility to access the values we iterate over. Those can return, in this case, just optional errors, expected void. So this is the way how they can return result. If something failed, then we can analyze the return code. If we are not writing generic code, we can use std function, the functions that return std function, again, based on type erasures. So we can provide the polymorphic function repo that will be then called within the iteration. One more nice thing to consider is that we also have structured binding. And if we have an object, and in our case, we have some form of the object that performs the lazy deserializations of the data. This is how our items are represented in our C++ API. So we have our views within the storage. Those are our byte spans here. And it, based on the serialization, deserialization traits, perform deserializations on demand when the key and value are called. The thing is that we do not want to call deserialization all the time. In some cases, we do not need to deserialize the object that we retrieve from the database. But but when the client wants to get those values, then it will be triggered. So that means that we perform it in a lazy manner. Yeah. So, but in some cases, it will be beneficial if the key and value are supposed to be retrieved, that we can use the structured binding syntax here. And this is also improves readability, but can be shared. So, and also available for the tuples already and for some other types. But for the custom types, the tuple-like protocol can be implemented. And this can be also, so this is not, so it's not involving that much of the complexity here. We actually need just to specify the number of the items that we are supposed to bind and the types of those items. Here we are just, those are the customization points, how we implement this. So for the custom type. And then we need to also have the get function that is available via argument-dependent lookup. And this is the thing, this simplifies the access to the items, make it compatible with the more modern syntax, and still supports the logic in which we are calling some APIs instead of actually just returning some items that are already compatible with the structured binding syntax. So one remark about runtime efficiency. So in this specific, in those techniques that we were reviewing, we did not use any polymorphism. Yeah, we also were not doing any dynamic memory allocation. Yeah, so within wrapper code. In C APIs they're happening, but we are not adding extra allocation. We also have some compile time logic that in some cases, so it doesn't affect the runtime. In some cases, it even minimizes the runtime. And generally, if we're using this generic approach where we have the class templates, so the code is likely to be lowered to just the API function calls. It's of course doesn't prove that there is nothing here in between, but so we do not inhibit the optimization. We do not have any indirection here. There are some extra codes because costs because we can have some extra ways of error checking here. But anyway, so this is will not imply really any dynamic dispatching or similar heavy runtime expensive features. So this will not be like this if we will not be using the generic approach. When we will be using std functions or something like this, then it will be a different picture here. Okay, now one thing, actually last chapter is about testing. We need to verify correctness of interaction with the wrapped API. Why? Because we want to protect the client from some errors, and we also do not want to make those errors within our wrapper code. We need to make sure that what we implemented, that the contract of interaction with the C API is that we follow it correctly, and we are not having actually errors within our that we are not do not make mistakes, and that we have everything implemented in a way how it was supposed to be used. And for this, yes, we need to use some approach. Some of the ideas that I would like to revisit, they were already showed in the talk, test-driven development of embedded and system-level software last year. There I try to elaborate in details about the different problematic of testing this code that is dependent on C APIs, but I would like to revisit a couple of techniques that are very relevant to this specific problem. So, but first of all, we need to figure out what testing strategy we would like to use. Yeah, so because we have various approaches. We can use integration testing, so that's when we will be testing our wrapper code together with the wrapped code, and we'll perform the same operation that the wrapped code is supposed to be able to perform and verify that it works correctly. Also, we can try to use unit testing, so we will be just testing the wrapper code independently. So we are trying to mock the API here. And most likely to provide sufficient coverage, both approaches are will be required. But if integration testing is quite simple, with unit testing of the code that is dependent on C functions, it is a bit tricky. So let's look at the techniques that we can use for unit testing. And unit testing in general can be beneficial because if the code of the wrapper supposed to have some logic apart from just forwarding the data there and back, like it is in most of the cases in our examples, then in some cases we can, in unit tests, we can trigger such conditions that cannot be just simply triggered in the real life. For example, various error code scenarios. In case of LMDB, for example, if we would have some logic to recover from some errors, it would be interesting to see how this code, how the wrapper code would react on the errors like that the file system cannot, that the read from file failed. But this cannot be simply emulated in the test environment. But in the unit test, this error can then be actually injected into the wrapper. So let's have a look at the unit testing approaches that we can use. In fact, we have only two options that will not have the kind of runtime overhead. We can use link time injection or link time substitution. This is a quite well-known technique, I think used since a while and even for C code. And we can also have compile time injection. For link time injection, it is the idea is that we take our the dependency framework that we wrap, we substitute the implementation by the test implementation. So for our LMDB functionality subset, what we will probably need to do, so we have our header included. We then can define a mock object that will have the methods that correspond to the methods of the wrapped API. Then we declare the functions to register this mock object. And in the implementation, we will have this global mock that will be a singleton for us. We will set it by those register and then register and reset by register and then register functions that we declared, and here we implement them. And the implementations of the C API functions will be forwarding the calls to the mock object. And then we will link against this implementation. So that means that we will be, so the calls to the C API then will be landing in the calls to the mock object. We will not be able to perform tests in several threads in one single execution unit. But anyway, this enables testability of such a framework. This is one of the approaches. This then can be also generalized with the fixture, where we can set up and tear down the mock. And in our tests, we set up the expectation of our mock. And here, for example, we trigger error that resource is busy and see how our code will react on this. So should return the corresponding error. Yes, this is one of the approaches. And it's actually enables testability, can be used to test actually even C code, and quite well-known practice for this. It is really well suitable for testing of C APIs. And it does not require any dependency injection-based design. So we do not need to redesign. It works quite well with some legacy code. And we do not have any runtime overhead because of this, because we just substitute the dependent code. So this is one of the approaches, but it requires those setup for the testing where we actually we need to deal with the re-implementation of the framework, and we need to carefully link against the proper implementation. Yes, so alternative approach, it will be some compile time polymorphisms, but a bit tricky one, because we do not have a way how we just can simply inject the function. So the function is we need to make our code generic in a way that it accepts some form of the proxy that will be calling the dependent API, or the dependency, the API that we depend on, sorry. And for tests, we can substitute this proxy by the mock. The idea here, we will do our code generic. It will be beneficial if we also specify a concept to specify what kind of interface we are dependent on. Here we are just describe the API, the C API that our proxy is supposed to represent. And our code should be written in a way that it can either own this proxy or can receive it as a reference. This can be achieved using combination of several techniques. So we need to have a constructor with perfect forwarding, and also template argument detection guide that would link the constructor parameter type to the template to the template parameter type. If we implement those techniques, the object that we store can either be a type or a reference. The same thing can be achieved using the function template. So generally here is similar. And the idea is that this would enable those use cases. When we create the object, passing there as a value reference the proxy, or we passing as L value reference the mock. For tests, we can pass the mock. For production environment, we can pass the proxy. And the proxy should be implemented in a way that it just forwards the calls to the C API. That means that we are not implementing this manually to avoid any potential errors, but just use the language features to do that. So we have a function template method. So in this case, it's a method of the proxy where we just perform the forwarding of the parameters. And this can be also generalized as the macro. Yeah, there can be different opinions on this, but I think this is a good application of macro here. And then we can attach some standalone functions to the methods. So we can specify the forwarding like this here. This that would then enable testability in the way that we can have our production API, or we can have our mocks. And in a similar way as before, we pass the mock instead of production API in the test environment and can verify the same logic as we verified before. This makes things a bit more, so actually things more complex, but it works quite well if there is a dependency on a couple of functions, for example, and we need to write some code and verify it. But and it's a possibility, and it's possible to maybe make it in some this code is isolated from the client access, because if those instantiations is handled by another code, then this is quite a convenient technique. In our case of LMDB, it's also important to take care of the lifetime of this proxy, and probably it will be owned by some root in our logical hierarchy, most likely somewhere in the deleter of the environment object. So this will not require any separate test environment. Everything works in the same way as we typically do for compile time dependency injections. And this can also be used, although it's a bit out of scope of this function, can also be used to mock C++ functions. For example, some static functions or the functions that are declared in the header that will not work with the this link time substitution. So some inline functions, for example, as well. Okay, so now let's go to summary. So what I wanted to highlight again, so even minimalist improvements using C++ features, they can actually significantly improve code safety. We saw that just using stronger types, using safe resource management, this would significantly contribute to code safety. Also, if we can adapt our C API to be used with just standard C++ facility, this is, of course, also beneficial. So that means that there is a high chance that it will be used, and it will be easier to use it. There will be much more convenient, and usability will definitely be improved. And one thing that I also want to emphasize again, that the bindings, they actually can and should be tested. So this is important. And that's basically all what I wanted to tell today. So let's switch to questions.